Chapter 7.3 and 7.4. So we're first of all going to be discussing something called the central limit theorem for sample proportions, identify the conditions and the need to apply the central limit, what's called the central limit theorem. Oops. I don't know what happened here. Okay. Here we go. Yeah. Conditions needed to apply the central limit theorem for proportions, and then use the central limit theorem for proportion to describe the sampling distribution of a sample proportion and to find probabilities. So let's begin by talking about the central limit theorem for sample proportions. This is used to estimate proportions in a population, and it tells us that if some basic conditions are met, the sampling distribution of the sample proportion is close to normal. This is very, very important here. Now, just about all of the samples that we look at are going to meet these conditions, but we still want to look at how to find them. We might take them for granted, but please know that they exist and we want to check on them. Now, if we take a random sample from a population, and if the sample size is large and the population size is much larger, okay, notice words here, sample size is large and the population size is much larger, then the sampling distribution of p hat is approximately normal with a mean of p and a standard deviation of the standard error given by that nice little square root formula that we use. If you don't know the value of p, then you can substitute the value of p hat, okay? If you don't know the p value, then you can substitute the value of p hat, which is the sample distribution. In other words, if you don't know the population p, then you can substitute the p for the sample itself. Now, these are the conditions that have to be met for what's become known as the central limit theorem. One is that the sample is random and independent. And the problem will tell you that it's random and independent. The second condition, very important condition, is that it must be a large sample. The sample size n is large enough that the sample expects at least 10 successes and 10 failures. That's the standard. At least 10 successes and 10 failures. In other words, n times p hat must be greater than 10, and n1 minus p hat must also be greater than 10. So we will perform that little test to see if that works. Huh? And big population, so large sample and then big population. If the sample is done without replacement, the population must be at least 10 times larger than the sample size. So if you have a sample of 10, then that population must be at least 100. Or if you have a sample of 20, then that population size must be 10 times or more than 20, which is 200. Here's an example. According to www.statisticsbrain.com, 59% of vegetarians are women. Okay, this is just a random sample here. Suppose a random sample, okay, random sample of 500 vegetarians is taken. What is the approximate probability that the proportion of the females in our sample would be more than 63%? So the first thing we want to do, we notice that the sample was random and independent. That's given in the problem. Next, we take the 500 times 0.59, and we see that's 295, which is a number that's greater than 10. Then we take, remember that's p hat, right? Sample n 1 minus p hat, and we see that that number is 205, which is also greater than 10. And then we can assume that there's at least 5,000 vegetarians in the population. Okay. From this information, you would calculate the standard error using your formula, and then you would use technology to compute the probability. Okay. So the technology, and I'm going to show you how to use that when we do the problem, but the technology would give you the probability distribution greater than 63%. Now, there's something called confidence intervals, and I want to elaborate on that in chapter 7.4, relatively short chapter. The Kaiser Health Tracking Poll surveyed 1,504 American adults and asked them if they supported or opposed the requirement that private health insurance plans cover the full cost of birth control. The poll found that 61% of respondents supported this requirement. What percentage of all Americans support this requirement? So we have a sample here, 1,504, and they want to know what percentage of all Americans actually support this. So you would go through the process here. The estimator p hat is 61%. Calculate the standard error. The sample size is large. The probability distribution is approximately normal and centered. Now, at this point, you would use technology to determine the confidence level. And again, I'm going to show you how to do that. The confidence level usually reads there's a 95% chance that P is closer to 2 standard errors away from the population. And, that 0.126 came from this number, 0.0126. So 2 times 0.126. So that number is going to be 61 minus 2.5 and 61 plus 2.5. Now, don't worry too much because those two percentages, that's called a confidence interval, but that's computed using technology, either StatCrunch or your calculator. So a confidence interval is a range of plausible values for a population parameter. Now, here it gets important. A confidence level which expresses or level of confidence that the interval contains the population parameter. Okay, that interval that we selected, where 95% is the industry standard. Okay, 95% is the general standard if you're not given a confidence interval. Okay. Confidence level tells us, now notice the difference, confidence interval versus confidence level. Confidence level tells us how often the estimation is successful and measures the success rate of the method, not one particular interval. That's important, and it comes back again in the definition. But the level measures that level, that 95% level, measures the success rate of the method. So I'm going to show you a couple of different ways to compute what we just had here. We had we don't. Okay. All right. So when I do the problems, I'm going to go ahead and show you how to do the computation. Okay. So keep that there. We'll come back on references. FYI, the relationship between confidence level and interval 99.9, 99.7. So this is 1 standard deviation, 2 standard deviation, 3 standard deviation, greater than 3 standard deviation. Okay, now let's look at some of the problems here. And like I said, I'm going to show you when we get to the confidence levels, I'm going to show you the confidence intervals. I'm going to show you how to do that with both the calculator and the StatCrunch program. Now, here we go. According to a candy company, packages of a certain candy contain 15% orange candies. Find the approximate probability that the random sample of 200 candies will contain 19% or more candies. So for the very first thing you want to do here is to compute the standard error. Remember, standard error is P into 1 minus P over N. Okay, and here P is equal to 15%, which is as a decimal 0.15, and N is equal to 200. Okay, so I'll go to my calculator. Second square root alpha y equal to get the fraction bar 0.15 into 1 minus 0.15 close parenthesis divided by N is equal to 200. So 200. Okay. Now, you want to go ahead and take this to 2 decimal places. So let's capture this, if we can put it into the notes. Okay. All right, so our standard error or standard deviation is 0. And take it to 3 decimal places. So 0.025. Yeah. All right. Now, to get the probability, we use StatCrunch. Okay, so you can also, and I've shown you this in the past, where you can also use your calculator, but we're going to go ahead and use the StatCrunch program. Okay, so data, statistics. Okay, data. Sorry, we're doing. Where is it? Statistic calculators, normal. And for the mean here, we're going to type in, the mean is given as, from this problem, 0.15, and we're looking for a number that's greater than 0.19. So type in 0.15. Standard deviation, we calculated that. The standard error is 0.025. And then we're looking for greater than 0.19. So we're going to type in 0.19 here. Then hit compute. And we're getting this answer of 0.05 to 4 decimal places. How many decimal places are they asking us for? So problem is asking for 3 decimal places. Now, FYI, note that if you take the standard deviation as 4 decimal places, your answer will be even more accurate. So let's say I took that as 0.0252. 0.0252. And I will get 0.56, which is also an accurate answer, right? So pay attention to what it's asking for. I can also go back on my answer here and approximate it and leave it. I'm sorry, what was this again? 0.025. Let's go ahead and put back what we had before. Oh man, I need to clear this out here. 0.025. Okay. If your answer is not getting corrected, you can probably go to 1 more decimal or 2 more decimals and see 0.0252 or 0.02524. Sometimes, depending on what standard error you're using, you will get to the correct answer eventually, okay? 0.025. I can add in another number here, say 2, 4, and compute it. And the more digits you add in for standard deviation, the more accurate your answer is going to be, okay? So I'm going to go ahead and put this in here. And, from this, we can get our answer here as to 3 decimal places, 0.057. Okay, greater than 0.19, 0.057. That's because I use the standard deviation to 4 decimal places. Standard error as 0.02524. Okay, I put 5 decimal places, so I got a really accurate answer. All right, moving right along. A recent study reported that 24% of residents of the particular community lived in poverty. Suppose a random sample of 300 residents are in this community. So n is equal to 300. We wish to determine the probability that 29% or more of our sample will be living in poverty. Before doing your calculations, determine whether this probability is greater than 50% or less than 50%. So again, the answer should be less than 50%. This is common sense because 29% or greater than the population of 24%, and the sampling distribution is approximately normal. That part is kind of cut out from there. But right there is your explanation. Should be less than 50%. And the reason, nothing to do with the z-score. Nothing to do with the z-score. should be less than 50% because 50%, 29% is greater than the population proportion of 24%. So the next part is asking us to calculate the probability of that 29% or more of the sample will be living in poverty. Assume the sample is collected in such a way that the central limit theorem conditions are met. So first thing, we want to calculate standard error. We know that the p-value is equal to, where is it, 24%. So standard error is 0.24 into 1 minus 0.24 over 300 square root. Okay, calculator. Over, what's that? Is it 300? Yes, 300. So over 300. And that's given me 0.025. Okay, I'm going to use 3 decimal places. So this is 0.025. All right, now I want for p greater than p hat, for p hat greater than or equal to the probability for p greater than p hat of greater than or equal to 0.29. So now I know my mean is 0.24, my standard deviation is 0.025, and this is where I would use the StatCrunch program. So I go back to the StatCrunch program. Here I'm going to put in 0.24. Yeah, 0.24. Okay, so that's my mean. My standard deviation is 0.025. So let's just clear 2 of the decimal places out. And I want to get greater than 0.029. Or 0.29, sorry, greater than 0.29. Compute. And I have 0.022. Okay. Now, FYI, if you want this number to be more accurate, then you can go with, notice that on this we had 0.202465. So if I went with 0.024, 4 decimal places, 0.0247, 0.0247 in my StatCrunch calculation. Okay. The 4 decimal places. When I compute this, my answer will be even more accurate. Okay. So be careful with how many decimal places you're taking. Copy the image, place it in here. Oh man, what did I do? Well, this thing's not behaving. Okay, so in this particular case, I put 0.0247. I took it to 4 decimal places to get a more accurate answer, and I got that value as the 3 decimal places they wanted as 0.021. Okay. All right, moving on. Problem 3, interesting question here. A true-false test has 140 test questions. A passing grade is 61% or more of correct answers. What is the probability that a person will guess correctly on a true-false question? Okay, so true-false question, you only have a 50-50 chance of guessing correctly. Probability then would be simply, instead of 50%, 0.5. Okay, 50%, 1 over 2. You either get it true or get it false. Guessing incorrectly, same probability, 1 over 2, 50%. Okay. Now, find the approximate probability that a person who is just guessing will pass the test. So to do part C here, we need to first compute the standard error. And we know that N is how many questions? 140 questions. And the standard error, sorry, the p-value is equal to 0.5. So standard error is 0.5 into 1 minus 0.5 divided by 140. Okay, calculator. Point 0.5, 1 minus 0.5 divided by 140 questions. So 0.042, okay, 0.042. Now, we need to go, and you can take this to 4 decimal places if you want, 0.0423 if you want a more accurate answer, okay? Now, let's go ahead and compute the probability that a person who is just guessing will pass the test. So P has to be greater than, remember the passing grade here is 61%. P has to be greater than or equal to 0.61. So go to our StatCrunch program. This is the mean is, so the mean is 50%. Yeah. The standard deviation is, where is it? 0.0423. And we want to get a score greater than or equal to 0.61. Okay. Now, it depends on what level of, if you took this to 3 decimal places, when you computed your answer might come out to be, say, 0.0044. Okay. All good answers. So if your answer is not going through, sometimes look at the number of decimal places and copy it, right? but this is giving me a probability of about 0.0044, which is great. I'm going to go with it. 0.0044. Okay, that answer right there. Now, the question continues. If a similar test was given with multiple choice question of 4 choices, would the approximate probability of passing the test by guessing be higher or lower? By the way, if you interpret that probability, this person has a 0.4% 0.4% probability of passing the test by guessing only. Now, if the person had 4 answer choices, it would be lower, not higher, because the probability of guessing correctly on each question is even greater because there's 4 questions now. Okay, so keep that in mind when you answer this question. If you had 6 options, the probability of that person passing would be even lower, and that's kind of again a common sense question. Okay. Question 4. If a sample is collected without replacement, which of the following conditions regarding population must be met to apply the central limit theorem for sample proportions? So the population must be at least 10 times bigger than the sample size. Okay. When applying the central limit theorem for sample proportions, again, which of the following can be substituted? I did this in the notes with you. Hopefully you guys remember that you can substitute the sample proportion. So we're getting into the confidence intervals now. To check the condition that the sample size is large enough before applying the central limit theorem, researchers can verify that the products of the sample size times the sample proportion and sample size are both greater than or equal to what number? And recall that this number is 10, right? That given number is 10. Okay, now this is a printout from a confidence interval report. A research poll shows that 129 out of 2018 randomly polled people in the country favor the death penalty for this convicted of murder. This should be those convicted of murder, right? Assuming the conditions for the central limit theorem were met, complete the parts A and B below. So I am 95% confident that the population favoring the death penalty is between these two numbers to 3 decimal places, 0.588 and 0.630. Question: is it plausible to claim that a majority favor the death penalty? Definitely, because that interval is between 58.8 to 63%. Okay, so it is plausible because it contains values above 50%. And remember, that's our standard. It must contain values above 50%. Okay, now we're going to go ahead and work a problem here to compute the confidence interval, and I'm going to go through this with you. A poll asked adults in a certain country whether immigration was a good thing or a bad thing. Out of 1,008 respondents, 400 said it was a good thing. What percentage of those taking the poll said immigration was a good thing? So good thing is 400 divided by 1008. Calculator. And that's approximately 39.68 or 39.7%. Okay, the 39.7%, one decimal place of those taking the poll said immigration was a good thing. Now, Part B wants us, this is Part A. Part B wants us to check to see if the conditions to apply the central limit theorem, if we can apply the central limit theorem. So we're going to assume, first of all, that the condition, the random and independent sample is assumed to be met. Okay, so one, the random and independent sample can be reasonably assumed. Okay, the large sample condition says that P has to be greater than or equal to n over P, n times P must be greater than 10. So n times P here is hold on 1 second here, I'm messing this up a little bit. Okay, so we're going to use our proportion here, 0.397 times 400. So 0.397 times 400 and then 1 minus 3.97 241. So in both cases, we're getting numbers 158. Let's say this is 159. And then n into 1 minus p. Sorry, this is equal to, not sure what I did there. .397 times, this is not coming out right. Let me put back what I had here. Calculator, print out. Okay, 1 minus 3.97 times 400. And we got that number equal to 241. So both of these numbers are greater than 10, which means the large sample condition holds. Large sample condition holds. And then with the putting 1,008 sample of 1,008. So 1,008 times 10 is 10,080, which is meets the idea. There are definitely 10,080 people in a large population in a country. And the United States has 300 million people, so this also holds. So big population. This is large sample, and this is big population. Now, to compute the confidence interval, let's look at what we have here. We have, and they're telling us this is 95%, and you have to stay with me for this. We have 39.7 of those, and we have 400, and we have 1,008. Okay, let's go ahead and put that into StatCrunch, and I'm going to show you how to compute that. So close this, and you want to do stat, proportion stats, one sample with summary. Okay, so let me do that again. Stat, proportion stat, one sample with summary. And you see this. Now, in this, you want to type your two numbers. The successes is 400, and the sample is 1,008. So 400 goes here. Then in the second box, the number of observations is 1,008. Next, you want to select the correct confidence interval, 0.95. And you can change that if you're given, say, 0.99 or 0.80, and compute it. Okay, now I'm going to copy this and put it into the answer place so you can see it. Okay, up, 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 up. Now what I want here, how do I copy this? Okay, that's not going to allow me to copy it. Click on output, drag the mouse to select. All right, I'm going to just use the snipping tool here, or handy snipping tool. Where is it? Okay, we can use that snipping tool to get what we want here. Okay, and I'm going to copy this over to the notes. So this is a little out of whack here. All right, here we go. All right, so the 95% confidence interval is based on this. The limit 400 1008. 95% confidence interval is between 0.367, 3 decimal places. It's this number here, and then 0.0427. Okay, notice that the calculator also calculated that proportion right there, that 39.7, in case you wanted to get it from here. Okay, the StatCrunch program did that for you if you wanted to get it from there. So this is saying that that interval is between 36.7 to 42.7. Now, if you wanted to do this with the calculator, you can also do that with the TI-84. Okay, press the Stat button, scroll over to Test, and you have to scroll down until you get to one sample proportion Z interval. okay? One sample proportion Z interval. Enter 400, enter 1008, and enter to calculate. And you pretty much get the same answer as if you ran the StatCrunch program. Okay, so this is the other answer here also. If you're using the TI-84, you will still get the same answer, okay? Either way, you'll get the same answer. Notice you can get the proportion and you can get the confidence interval from this. All right. Question 9. A poll reported that only 1,579 out of 2,255 adults in a particular region said they had a great deal of confidence or quite a lot of confidence in the military. Assume that the conditions we use in the central limit theorem are met. Okay. Find a 95% confidence interval that expresses a great deal of confidence or quite a lot of confidence. So part A, we're just going to go straight to StatCrunch, 1579 and 2255. Okay. And then for a second box, we're going to type in 2255. 95% compute. And let's snap this over. So we have, I'm going to put this in here. See if I can drag this over a little bit. All right, we've got, I don't like how this is coming out. No, let's see if we can make it a little smaller first. Yeah. Much better. So we've got a 0.681 to 0.719. Again, remember you can use your calculator for this if you want to simply follow the process. Stat, test, scroll down to, what did I do? Stat, test, scroll down to one proportion Z interval, and type in your two numbers, which in this case was 1579 and 2255. Enter, enter, enter. And it will give you, oh man, what did I do? I think I messed up something here. Okay, here we go. Okay, there it is. 0.681. So you can also use this if you want to use the TI-84 program. They're both very easy and straightforward to use, okay? All right, now the interpretation of this is that we are 95% confident that the population of proportion of adults having greater confidence in the military is between 0.681, and 0.719. That's how you read it. We're 95% confident. Now, if you wanted the confidence, for the confidence 80%, all you would do is go to that StatCrunch program and edit it and change the level from 9.95 to 0.80. And compute it, and you would get a new confidence interval here. So let's copy that as well and put it over. This is part B. Okay, part B, which is showing between 0.688 and 0.713. And remember to do this in the calculator. You would use stat test, and then scroll down to 1z proportion test, 1z proportion interval, and change your confidence level to 0.80. And it will provide you with exactly the same answer, okay? In fact, sometimes the calculator is just a lot faster to do this than the StatCrunch program, but that's up to you, whatever you want to use for it, whichever one works better for you at the time. Okay, so we're reading this again. We are 80% confident that the population of adults have a great deal or quite a lot of confidence in the military is between 0.688 and 0.713. Just notice the wording, 80% confident, okay? And it's not a sample, it's a population. Same here, not a sample, always on the population. The question continues, which interval is wider? The width of a 95% confidence interval, is it wider than an 80%? So we see that between, for 95%, okay, for 95%, the interval is between 0.719 minus 0.681, and that's equal to 0.719 minus 0.681. Not right. 0.719 minus 0.681. So 0.038. And then for the 80% interval, it's 0.713 minus 0.688. 0.713 minus 0.688, which is 0.25. So obviously the 95% interval is wider than the 80%. Oh, I'm sorry, they're asking us the numbers. This one is 0.038. And the width of the 80% is 0.025. I wrote that wrong, 0.025. So the 95% one is wider. Okay. Question: how would a 95% interval compare? So it appears that the higher the confidence interval, the wider the um, the wider the width of that interval. So let's see, a 90% interval would be narrower than a 95%, but wider than an 80%. Make sense? And 90% would be wider, and you can actually check that. If you wanted to do a 90%, simply go to the calculator and change that to a 90%, sorry, a 90%, and change it, and you'll see exactly what I'm talking about. So if I changed it to a 90%, I would get 0.716 minus 0.684. Oh, that 0.716 minus 0.684, which is 0.032, which is narrower than 0.038, but wider than 0.025. Okay, let me write these two numbers down, 0.716, 0.684. Okay, last question is asking you, which of the following does the confidence level measure? Remember, I kind of emphasized this in the notes. It simply refers to the success rate of finding the method of finding the confidence intervals. Okay, I know this has been kind of a tough lesson, and I hope you guys were able to follow me. Let's go ahead and finish.